Hello everyone, I'm Yu Wang from Samsung Research America. Today my presentation title is an interactive adversarial reward learning-based spoken language understanding system. So the work is together with my colleague Yilin and Hongxia, both from Samsung Research America. So here is an overview of my today's presentation. First, I will give a background overview about the multi-round semantic frame parsing. And then I will give all the details about the interactive adversarial reward learning SL system, which is introduced in our paper. And the system contains 5 main components, including the feature generator, slot extraction model, reward estimator, the adversarial discriminator, and the slot filling table. And finally, we will demonstrate the system's performance by using 2 experiments. One is a single round SLU task. Another is a multiple round SLU task, which is also a flight booking task. Okay, so let's take a look at the multi-round semantic frame parsing. So traditionally, the dialogue state tracking model is used to handle the multi-turn responses. And the target of these models mainly contain the following 3 topics. One is for the topic changing, and another is the multi-domain adaptation, and the third one is improving the goal accuracy. And in our paper, we mainly deal with the so-called multi-round semantic frame parsing. And the main difference between the multi-round semantic frame parsing compared to the dialogue state tracking is the following 4 points. The first one is that there is mainly no topic changing in the multi-round SAU task, spoken language understanding task. And also there is no domain adaptation. And furthermore, and the most important is that the system feedback is not part of the training data. And also that the feedback is not necessarily in text, which is quite different from the dialogue state tracking task. So that's why we developed this interactive adversarial learning SLU system to deal with mainly the multi-round semantic frame parsing task. So let's take a look at the overview of the vSharded for inner loop system. And as I mentioned before, there are mainly 5 submodules. One is the feature generator, is here, and also we have this adversarial discriminator, and also the reward estimator, and also we have this slot extraction model, mainly used by leveraging the reinforcement learning and the RN tagging model to extract the corresponding slots from our user query and also the user feedbacks. And the last one is the slot filling table, basically to find the corresponding mask labels and generate the final outputs. Okay, so I will explain the 5 submodules one by one. The first one is a feature generator. So the feature generator is used to extract the semantic features from both the original query and also the user feedbacks at each round. We represent it, for example, like a round T. And also it's used to estimate the reward R and to generate the policy pi and the state ST in the slot extraction model. So for the feature generator, we encoded both the original query and the user feedbacks by the attention bidirectional RN structure. And the original query is represented by CQ, and the user feedback at round T is represented by CFT. Okay, so the output of the feature generator is a combination of the 2 vectors, which is the CQ and also the CFT. It's a combination of the 2 vectors that's shown in the figure here. So the second main component in our system is we call it the slot extraction model. And for the model itself, it contains 2 submodules. One is the reinforcement learning based policy model, and the second is the RN tagging model. So the combination of these 2 submodules is because that we use the policy model to decide that what are the which part of the generated RN tagging tagging models labels, or we call it slot candidates, should be kept or should be removed. So as shown here, the RL policy model generate the policy pi B and the masking rules. That is the ST. So the masking rules, the state ST is like this. So for each entry of the state ST contains a binary value of either 0 or 1. So the 1 means that the ith label in that row, Li, so that should be presented. Or like the 0 means that the ith label Li in that entry should not be presented. So to represent this mathematically is that ST is equal to LSTM function by taking the concatenation of the user input and the query and the user feedback as a time step P, and also the last time step state or the last time step masking rules. Okay, so F here stands for the LSTM unit, and G here is multi-layer perception for the original query and the user feedback matching. Okay, so basically this mask is used to decide that what are the tags generated by this RN tagging model, or what are the slots generated by this RN tagging model should be kept or not. So then the second part of the slot extraction model is this RN tagging model. Okay, so it extracts the slot matrix from the concatenated queries, and the ith row of the output of the RN tagging model, which we represent as C slot T, represent the average sum of the label token embeddings under the ith label Li. And if there is no token under the label, then the labels row is padding by zeros. Okay. And also the final output of the slot extraction model is the mask slot matrix MT, which is the final slot matrix after masking by taking the dot product of the diagonal matrix of ST and the C slot T. So diagonal ST basically is the diagonal matrix, which is diagonal element as STI, and all the elements are zeros. So basically it's used to mask the generated slot candidates. Okay. So another very important component in our system, we call it the reward estimator. So the reward estimator is working together with our another component, which we call it the adversarial discriminator, and to estimate the reward in our reinforced learning function. The reward estimator R theta is a nonlinear function by taking kernel round mask slot matrix and user feedback feature vectors CFT as its input. Okay, so here phi is a nonlinear function, and the MT CFT stands for the projection of the feedback feature, which is the user feedback feature as the round T to the slot filling representation matrix MT, such that it can be used as part of the information to generate our reward. Okay, and F is a LSTM function, and W and B are the weights in our nonlinear function. Okay. So in order to train the nonlinear reward function, we leverage the adversarial discriminator to associate the generated mask slot matrix with the reward function approximated by the Boltzmann distribution probabilities. Okay. So the optimal. So here is the p theta represent for the reward Boltzmann distribution, and to approximate the data distribution. So the optimal reward function R star. So the R theta basically is estimated reward function, right? So there is an optimal or our target reward function R star is achieved when this reward Boltzmann distribution P theta is equal to the real data distribution, which is P star. Okay. So the objective function is a min-max function represented mathematically as this. So the function, as you can see, that the function is a min-max function, and is to maximize the p theta similarity with the empirical distribution of the training data PE. and also to minimize the similarity between them and the data generated by our slot extraction policy pi beta. So that's why we say that it's as an adversarial discriminator by using the min-max approach to estimate the reward. Okay, so the final component of our entire inner loop system is we call it the slot filling table. So the slot extraction model sends its output empty to the slot filling table, such that it's going to update its slot entries and then use to send it to our backend database and extract the corresponding answers. So at round T, the new table values is by adding the new extracted slot entries from MT to the table T -1. So basically here is a union function by adding more extracted slot entries from MT to the new table T -1. So the slot values in the slot filling tables are combined into a format query by using a predefined templates and then sent to the backend database to fetch the result. So the backend database can be an API, for example, in our case that we are using the flight booking as an example, and so that we use the Google Flight API as our backend database to fetch the result. Okay, so then let's take a look at the experiment. First, I would like to introduce a data set, basically two data sets. And one is the standard ATIS data set, which is a commonly used data set for the spoken language understanding. It contains almost 5,000 utterance and 127 different slot types. Okay, so for that is basically the data contains mainly the flight booking utterance collected from the users. And these queries are more like book a flight from place A to place B, so like this. And the slot type is like the leaving city and also the arrival city and the leaving time, so like this. And we use these data sets as our basic data set. And then we expand this data set to a new data set called the augmented multi-turn ATIS data set to serve our multi-round semantic frame parsing purpose. So basically, the third curve will generate the 1 to 4 rounds of feedbacks based on the query in the standard ATIS data set. And in average, we calculate average of the feedback rounds is the 3.2 feedbacks per query. And what type of feedbacks are given by the Turkers? We have two types of feedbacks. One is that we ask the Turker will ask for extra information if the user query is not complete. For example, if the user wants to book a hotel, but he doesn't mention that what time and where to book the flight, book the hotel, and then the Turkers will ask for extra information about the time and also the place. And also that if it's the previous stated information is not that accurate or is a bit ambiguous, the Turker can also ask to update and correct the previously stated information. So here is our first experiment. The first experiment is a one-round user feedback experiment for flight booking. And the Turker will provide one round of correction feedbacks during both training and inference. And for example, like during the training, we first check whether the template-based result generated by the slot extracted from the original user query can fetch the correct result from the backend database or not, which is our Google Flight API. If the result is wrong, then our Turkers will provide feedbacks to the to correct the mistakes specifically, that is during our training. So as we see that in the experiment result, okay, so here that we use two different models, baseline models. One is attentional bidirectional RN, and the other is a slow-gated bidirection RN. I think the second one is published in 2018, and the first one is in 2016. And both of them achieved the state-of-art performance during that time, back to that time. And both of them are kind of famous SLU models that are commonly used as a baseline in today's research. So we can see that by using this as a baseline, these models as baseline, and adding our inner loop system, we can achieve that much higher slot FOI by taking the one more round users' feedbacks. and then also the a much higher sentence level accuracy by taking one more round of user feedbacks for both baseline models. And then let's take a look at how does this work if we add like several more rounds of user feedbacks, whether the slot F1 can further improve or whether the sentence level accuracy can further improve. So here comes to our second experiment, which is a multi-round flight booking task. In the multi-round flight booking task, the cookers provide a multi-round feedbacks during both training and inference. And as I said before, it's like there are two types of feedbacks. One is to ask extra information, and the other is to update and correct the previously stated information. Okay, so as you see that in this table, that again is for the first round is the same, and we have the inner loop model. The model with inner loop system is achieve better than the baseline, and you can see that when the round increase and the F1 score of the model with the inner loop decrease a bit and later an increase. But if you take a look at the gap between the baseline model and the model without the model with inner loop system, we can see that actually the gap is increasing when the round number increase. So that means that the baseline model and the baseline model plus the interloop system, this gap between them is become larger when the number of rounds increase. So that's mainly because of the when we have more information, the original more information by taking into more rounds of user feedbacks, the original model cannot handle that too well because there's extra informations that its model are not good at, and some of the information that models doesn't even know, that they haven't seen before. But our inner loop system can leverage the multiple rounds information by taking the multiple rounds user feedbacks, which is the original model is cannot achieve or not good at. Okay, so here is a conclusion of our model, of our paper. So the first is that we introduced a novel interactive adversarial reward learning based spoken language understanding system that can leverage the multi-round users' feedback. And also we show that our inner loop system can greatly improve the tagging model's performance with user feedbacks. And lastly, and also most important, is that the advantage gap of the inner loop system over the baseline become larger when the number of feedbacks round increases. Okay, so that's all for my today's presentation, and feel free to reach out to me if you have any questions. Thank you.